Hi there, everyone. We're going to talk around two new differentiation rules today. So firstly, if you've got f of x is equal to the exponential function e to the x, then the derivative is also e to the x. That's quite a remarkable property of this function. And we'll talk about this other rule as well, that if your original function is log x, then your derivative, or f dash of x, turns out to be 1 over x. Okay, now I'm going to talk around this for a bit, and I'm going to talk about e as a number. I'll talk about the sort of practical meaning of this on Desmos, but I'll also talk about the second one, the practical meaning of that on Desmos as well. So there's going to be a fair bit of chat and a fair bit of theory before we get on to the example 17 and the example 18. Should you just wish to skip forward to the mechanics of this, then you are welcome to. Okay, so first of all, we've got here this number e is turning back up again. And just to go back through a bit of history on this, well, we have, so this is known as Euler's number or Euler's constant. And this is a constant number, a bit like pi. E is the number 2.71828, and obviously carries on. It's an irrational number, just like pi, and it can't be defined by the solution of a polynomial, for example. So, okay, so what's quite interesting about this number is that if you do 1 over 1 plus 1 over 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3, and so on, let's go back, I need to do that, then called, right? So if you sum that, so there's the sum here, then if you tend that to infinity, so obviously you're getting a term at the end which is extremely small and adding almost nothing, then you're getting close to this number here. You could do that by setting up an Excel spreadsheet if you wish to. And also it's kind of interesting to note that the factorial of n, when n is equal to 0, is equal to 1. So 0 factorial is equal to 1. And if you want to know what factorial means, for example, 3 factorial means 3 times 2 times 1. 5 factorial means 5 times 4 times 3 times 2 times 1. Okay, so there's one way of expressing it, but there was another way of expressing this, which was developed by Bernoulli, I think. Yeah, Bernoulli, back in the 17th century, and that's this way here, saying the limit as n tends to infinity of, of 1 plus 1 over n to the power of n. And again, you could set this up on Excel perhaps, so you're tending n to a large number here. It may be that Excel would crash as soon as you get to sort of to the power of 10 or something or other, but you could try it out. Okay, so for example, 1 plus 1 over 100 all to the power of 100 is going to be a closer approximation than if we use 99. And obviously you use 1,000 and 10,000 is going to get closer and closer. Okay, well that's the number, that's Euler's number, but we're actually talking about the exponential function here. And turn out that who came up with this? This was Euler, of course. Euler said, well, exponential of x, in other words, e to the power of x, that's the thing here, is equal to, well, similar to this original e number, but he's put in an x there, and that's turned out to give us our function. I'm not going to go too much into that. I'm obviously going into quite a bit of detail already. Right, okay, so let's look at the graphs then. So the remarkable property of e to the power of x is that the derivative is the same, right? And so what I've set up here at the moment is g of x, you can see at the top here, g of x is equal to a to the x, and I've set a to be equal to 2 here. So this is currently representing the function 2 to the power of x. You know that because you're getting the coordinate point on here, 1, 2. So 2 to the power of 1 is 2. And of course, if you do 2 to the power of 2, you get 4. And if we did 2 to the power of 0, you're going to get 1. If you did 2 to the power of -1, you'll get a half, and so on. Okay, that's roughly there. Okay, so if I press play on this one here, we can see I've just chosen a particular coordinate point, and I've chosen a to bounce between 1.5 and 4. So now I've got different exponential equations here, but we have the base number is A. It's changing. It's not E in this case. E is somewhere there. It's somewhere. Just put it in there. Somewhere around here. Okay, 2.78, something like that. Okay. So if we put on our G dash of X, well, actually, let's just put on first of all. Let's play this through a little bit. So let's just play it to here. Okay. So at this point here, we can see this green dot is now representing the derivative, the gradient of the blue dot. So I put that on there. So that's G dash of whatever A is. And I've chosen, so G dash of X, and I've chosen X to be equal to 1. Okay, so if I bring this across, right, so if I bring this up, the blue point now, we can see that the gradient is 5.167, but it has a height at this point of 3.84. This is 3.84 to the power of X, this function. Now, if I bring this down, can I bring that back? Yeah. Right, if I bring this down, right, so down here, you can see that the gradient at that point is now less than the height itself. But at the point of, let's bring that up, 2 point roughly E, basically. So when I'm choosing A to be equal to 2.78, that's roughly E, we can see that the gradient is actually the same at that point. So it's the same steepness as the height itself. Okay, and now if I add in my G dash of X, in this case, and if I play this thing here, you can see that when we're above E for A, then the gradient line is above our original line. And when we're, let's stop it there. Okay, and when we're below, when A is below E, then we're getting a gradient function which is below. But of course, when we choose that actual function itself, if we choose G of X to equal to, let's say, E to the power of X, let's just delete that. Sorry about this. E to the power of X, we can see that the functions are now the same. Let's get rid of this. Let's get rid of this as well. Let's get rid of this. We can see that the two functions are now exactly the same. That is to say, G dash of X is the same as E to the power of X. Okay, right, and this is the only exponential function where this is working, and this is the original exponential function, if you like. This is E to the power of X using Euler's number. Right, okay, I've gone on a bit for that one. I'm going to go on a bit for this one as well, just briefly. This is log of X. The red graph here, this red graph is log of X. And you can see in this case that we have a gradient at 1, 0 of, and I've put in this line, the blue line here. We can see that at this point we have a gradient of 1. Okay, and you can see that after that we have a reducing gradient, but it's always positive. It never gives us a negative answer. It always stays positive for the graph of log of X. And you can see that it's always positive. There's the graph of log of X going down here. You can see that it's always positive down here, but it's extremely steep down here. So if we wanted to plot the gradient line, we're going to go through this point here. So it has a gradient of 1 at this point. So at 1, you're going to have a gradient of 1. But then we're going to have extremely steep gradients at this point, steep and positive. So we're going to have a high number up here. It's going to go through 1 here. And then it's going to get more and more shallow, but it's never going to be 0 or beneath 0. So it's going to go down to somewhere around here. Okay, so if we actually show the graph of f dash of X, there's the graph. So we knew it was going to be steep, the gradient at the start. Let's get rid of the blue line now. It's going to have a gradient of 1 at this point here on the red line. And there's a particular point where it meets. And it tends towards 0, this gradient. Now, in fact, this is the line, and I will say nothing much more than this. This is the line of 1 over X. This is the same. Let's see if I can write it in there. Let's put it in as another function. This is y equals 1 divided by X. You can see that it's only valid for, not on the left-hand side here, but only when X is greater than 0. I could put some conditions on that. I could say when X is greater than 0, because of course log of X is only valid when X is greater than 0 as well. So the derivative of f of X, let's just put this one in as well. Derivative is the same as 1 over x. Okay, right. Well, thank you for listening to all of that. Now we're actually going to do some questions. So let's go to, let's pick out these questions here and use those rules. So, okay. So first question, example 17, I'll do this one myself. So we can see, find the derivative of this first function here. Now you can see that again, they're starting to use straight away. They're not saying keeping it easy here. They're going straight into using the product rule, the quotient rule, or the chain rule. So in this question, we can see we're using the product rule. So we've got u is equal to x. We've got v is equal to log x. We've got u dash is equal to 1. And we've got v dash is equal to 1 over x. That's using our rules which we've just gone through. Okay, so we know the product rule is u v dash plus v u dash. So we're getting dy dx in this case is equal to, well, u is equal to x, v dash is equal to 1 over x here, and v is equal to log of x, and u dash is equal to 1. So we can times that by 1 if we want, but it's kind of pointless. This gives us the same thing. X times 1 over x gives us 1, so we get 1 plus log of x in this case. That's our derivative function. Okay, well, let's just have a little check of what they've done. Yep, they've got exactly the same thing, and they've just said how it's worked using the product rule. Okay, second question here, so let's get rid of that. Okay, and right, second question. So this one we can see we have a function inside a function, so we can write this one down as e to the power of u, or u of x if you want to. You can call it like that because u is a function of x. I'm just going to write e to the u. Right, for this question, remember the chain rule is dy dx equals dy du multiplied by du dx. And we've got y equals e to the u, so dy du, so differentiating with respect to u, it's going to give us e to the u again, and u is for x, and so du dx is equal to 4. Okay, so let's put these things in here. So we're getting 4 for this. So I'll put that at the front, and then we're getting e to the u, and I'll put in what u is again as well. So let's put that back in. We're getting e to the 4x. This is a really common format. Basically, a lot of you are going to get super quick at this, or you should all get quick at this. And so for this one, we can see it becomes e to the 4x, so it stays the same as e to the power of x stays the same. But because we've got a function inside the function, we need to times by the derivative of this thing inside. It's 4. Okay, so that's just an application of the chain rule. Okay, next question on this one, question 18. Let's go to this one, question 18. So this one's saying find the derivative of f of x rather than y is equal to sine of log of x. So again, we can see that we've got the chain rule in this case. We can see that u is equal to log of x, and u dash is equal to 1 over x using the rule that we have. And we see we've got this is sine of u. Okay, so when we differentiate this, let's do it fully, dy dx using the chain rule, so let's put it in. That's dy du dot dx. Okay, let's write it a little neater. Okay, and then we're getting, so dy dx is going to be equal to, or dy du, so we need to differentiate this thing here. That's still, sorry, not sine, that's cosine of u, and u in this case is log of x. And then we're going to times that by dy du dx. Du dx in this case is this thing over here, it's 1 over x. So we're getting 1 over x here, although I bet you they use divided by x in this case. So let's have a little look at this. Yeah, okay, so they've done exactly the same thing. Okay, guys, well, try to get maximum practice on this. They're all really important questions. It's really important that you get quick at this. Thank you very much for listening.